Hello. In today's video we're going to be going over the states of matter. So hopefully, as you guys know, there are 3 states of matter, or 3 states we really care about in this class. So those 3 states are gas, liquid, and solid. Okay. Each one of these states of matter are going to have their own properties that are unique to those states. And going between states, we're going to call that a phase change. So a phase change is a change of state. Okay, so we're going to look at our different states. We're going to look at the properties of those states, and then we'll look at changing those states, what changes between them, how we go through them, and energy required to do so. Okay, so here's just a little table that we're going to use to go over our different states of matter. So we have gas, liquid, and solid. We can look at them in terms of the flow of the particles or molecules, the ability to compress, the volume, shape, and density. So gases themselves, those are going to be the first one we'll look at. So gas particles are free-flowing particles. They are going to be very, very far away from each other, so particles are far apart. And we talked about in a previous video in intermolecular forces. And when we think about gases, we usually don't think about intermolecular forces. There's nothing really holding gas particles together. So we would say that the kinetic energy of a gas is going to be significantly larger than the intermolecular forces or attractive forces that hold particles together. So to be a gas, either we have to have a lot of kinetic energy or very, very weak attractive forces, or really a combination of both. Because these particles are so far apart, they are very compressible. So we would not consider a gas to be a condensed state of matter. Liquids and solids, we consider those to be condensed states of matter. Gases themselves, the particles are going to be very, very far apart, so we can compress them pretty significantly. With a gas, we're going to assume the gas particles will assume the volume and shape of their container. So we would say that a gas has neither a definite shape nor a definite volume. And then because these particles are very, very far apart, we would say that they would have a very low density. So the lowest of any state of matter. Next, we'll look at a liquid. Liquids, they're still pretty free-flowing. You're going to have your particles sliding past each other. So they're going to slide past each other freely. And here we do have attractive forces, right? We have kinetic energy and attractive forces, but we're going to go, we have a stronger attractive forces than we have in a gas. So stronger attractive forces, keeping them close together, and lower kinetic energy. I'm just going to put Ke for kinetic energy because I'm being lazy. Okay, with liquid particles or liquid molecules, there's going to be very little space in between them, so they're not going to be compressible. So we're going to call them virtually incompressible. Okay. And then we have a substance that is free-flowing, but we have a very definite amount of it. So we have a definite volume, but our substance itself can assume the shape of the container. So we're never going to be able to double our volume of our liquid or, get a larger volume of liquid. But we have an indefinite shape, so we're going to assume the shape of the container. And then particles are a lot closer together, so this has a high density. Okay. And our last state of matter is our solids. Our solids are in a fixed position. All of the substances, all the particles, all the molecules, all the ions, whatever it happens to be, they're going to be fixed. So they have a fixed position. Okay. They do vibrate though. So they vibrate in place. Here, we are going to have very significant attractive forces and very low kinetic energy. So we say that our kinetic energy is much smaller than our attractive forces. Okay, so in a solid, we have a lot more attractive forces than we have kinetic energy. Again, these are going to be fairly close together, so they'll be virtually incompressible. Okay. And here we have things that are fixed in position, so we're going to have a definite shape, and we're not going to be able to double the volume just by changing our container, so we will have a definite shape, definite volume for our solids. And with a solid, this is generally, though not always, but it is generally the highest density state. There are a couple of examples where this is not true, like water, but generally we're talking about them being the highest density. Okay, so going between phases, so our phase changes or changes in state, transforming one state of matter to another. Remember, a phase change is a physical change, not a chemical change. We still have the same identity of substance. So a phase change is just a physical change. We are not changing our substance. Okay. So anytime we go between states of matter, we have to understand that they have different energies, right? So our solids have the least amount of energy, our liquids have a medium amount of energy, and then our gases have the greatest amount of energy. So to go between our substances, we have to add or remove energy, or to go between our phases, we add or remove energy. Okay, so let's look at this diagram right here. Wow, that didn't come out very well, but we have a solid, a liquid, and a gas. Okay, so when we're going in this direction, we are going to add in energy. So this is going to be endothermic. So adding energy. And then going in this direction, we're going to remove energy. So it's going to be exothermic. So keep in mind the symbol or the sign for endothermic is always going to be positive. We're going to be adding into our bank of energy, and exothermic will be negative, removing from our bank of energy. Okay, so first let's look at going from a solid to a liquid. That is called melting. And then going from a liquid to a gas is called evaporation. Going back, gas to liquid, condensation. And then liquid to solid, we call this freezing. Usually people are pretty good with those four. Going from a solid to a gas, a little bit harder, but called sublimation. And then from a gas to a solid, we call this deposition. Okay. So, going between these states requires energy, or requires a changing of energy of the state itself. We call that the enthalpy of phase change. So energy required to change phase. Okay, so we're going to go from solid to liquid, liquid to gas, solid to gas, and we have different names for those energies. So if we're going from our enthalpy is going from a solid to a liquid, we call the energy there the enthalpy of fusion or heat of fusion. Okay. So it would be delta H FUS. It's going to be positive if we're going from solid to liquid, negative if we're going from liquid to solid, right? Because going from liquid to solid, we are actually removing energy from the system, so it would be a negative. Going from a liquid to a gas is going to be enthalpy or heat of vaporization. Okay, so that's delta HVAP. Okay. Again, if we're going from a liquid to a gas, it would be positive. Gas to liquid, it would be negative. And then we can go from a solid to a gas. And that'll be our enthalpy or heat of sublimation. So delta H sub. Okay. These energies that are required will be dependent a lot on our intermolecular forces, right? The greater our intermolecular forces, the harder it is to separate substances. And we're also, if we're looking at ionic substances or metallic substances, we can also look at the intramolecular forces. But generally, we're thinking more on the lines of covalent substances, molecules. So we're thinking about removing or softening our intermolecular forces. So the magnitude of the enthalpy of phase change for a covalent substance depends on the intermolecular forces that hold them together. Greater intermolecular forces will result in greater enthalpies of fusion, vaporization, and sublimation. Also keep in mind, generally liquid to gas or solid to gas will be significantly larger in magnitude than solid to liquid, and that's because when we're going from a liquid to a gas or a solid to a gas, we are completely breaking all intermolecular forces. Going from a solid to a liquid, we're just kind of softening those intermolecular forces. Intermolecular forces still exist in a liquid. They're just generally a little bit further apart. Okay, so looking at these energies, we're going to actually do calculations for these energies in a different video, but we are going to look at what's called a heating and a cooling curve to actually put all of these ideas into place to look at the energies and temperatures of phase changes within a substance. So if we have a heating curve, and I'm going to show one right here, we're going to look at several different things. We're going to be looking at all the different parts of, or all the different phases, the types of energies we're looking at with these, and we usually look at a heating curve in terms of temperature versus heat added. Cooling curve would be temperature versus heat removed. So our left and left bottom, lowest temperature, least amount of heat. So we start here at whatever temperature we want to start at, but we start as a solid, right? So we have a solid at some temperature, and as we increase in temperature, we're going to increase in the amount of heat added to the substance until we reach our first point on our heating curve. This first point is going to be our melting point. Just put MP for melting point. Once we reach that melting point, we then must add additional energy in. Okay? We do not automatically go from solid to liquid once we are at the melting point. We have to add in that energy, and that energy is that enthalpy or heat of fusion. So when we level out, we stay at the same temperature, but now we are softening those intermolecular forces right here. So this is our delta H of fusion. Okay. So adding in that energy, we go from our solid state to our liquid state. And right along this line, this heat of fusion line, our solid and our liquid are in equilibrium. I'll talk about that a little bit more when we start talking about phase diagrams. Okay, so once we've we've put in all the energy, all the fusion energy, we are now in a liquid state. Okay, so again, it's going to go up into a point. So all throughout here, we are a liquid. Right, so solid, this is solid, liquid equilibrium, and then we get into the liquid phase, okay, and then right here, this right here is going to be our boiling point, okay. And then we add in our heat of vaporization. Generally, more energy is required here, right? Because now we're breaking all of our intermolecular forces. So we're gonna quick move this. Oop, nope. Move that down a little bit to right there. Okay. Just wanted to put that right there. Okay. Once we reach here, we are in a liquid gas equilibrium. So as we add in that energy, converting from liquid to gas, we stay the same temperature until all of our liquid particles have been converted into gas particles. And then after that point, we are in a gaseous phase. Okay? You guys will be required to make one of these, so hopefully you have paid attention and know what's going on here. Okay? The other thing we can do is we can look at a cooling curve. So a cooling curve will be the opposite, right? So we'll start at a gas until we reach our boiling point. So our gas, this is our boiling point. This is negative delta H of vaporization because now we are removing heat, right? And then we go down until we reach our melting point. And then a negative delta H of fusion. And then back down to a solid, like so. When we're changing temperatures between solids, so going from one temperature of a solid to another temperature of a solid, one temperature of a liquid to another temperature of a liquid, one temperature of a gas to another temperature of gas, we're looking at specific heat, and I will do a specific heat review so we can actually do calculations with that. Okay, well, that is it for this video. Bye, y'all.